Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 30, part C, the final part of our exponential distribution. So last time we covered the mean, the variance, and went over an example of how to solve a problem with the exponential distribution. And we're going to continue this time talking about a very important property. And this is listed as a remark. And I've gone through, instead of just showing you an example, I've actually gone through the derivation to show this and prove this in a general case. So if a component, and we use the exponential distribution sometimes to model reliability of components. Specifically, this says electronic components. These are components that have what we call a constant failure rate. Remember that the mean time until the first failure is theta. And so electronic component, if it fails, it's gone, usually. There's not very much chance of most electronic components of fixing them, but some you could. So it just depends. But anyway, this is not the best reliability model, but it is a reliability model that is applicable in some situations. Okay, so if the component follows an exponential distribution, it has already survived x units of time. Okay, so it's already survived some time in operation. We want to know what's the probability it will survive y more units of time. And so that is given by a conditional probability. So the probability that x is greater than little x plus y, given that x is already greater than little x. So let's write out that and see what we get. So this is the statement again. I wanted to write it clearly so we could see. And then we're going to take, remember, we take the intersection of what's over here and here. If we call this A and this B, we take the intersection of A and B. And so here we have A, which is x is greater than x plus y. And here we have B, which is x is greater than x. Let's draw a little picture here. And let's say this is 0, and this is x, and this has to be x plus y. Remember, time is greater. So x, and we're saying that the first one says that it's greater than x plus y. And the second one says it's greater than x. So we want the intersection. We want where these two things are the same. I hope you can see from this picture that that is this right here. This is the intersection. Here, in between these two, is only true for x greater than little x, okay? It's not true for x greater than x plus y. But from here forward, it's true for both, that x is greater than little x and x is also greater than x plus y. So if you need to draw you a timeline like that, do so, because it's really important that you get this correct. All right, so we have that this intersection is now reduced to the probability that x is greater than little x plus little y, divided by the probability that x is greater than x. So this would work for any distribution. We would come to this conclusion for the conditional probability. So remember that. So now let's look and see. I say recall, but I don't think I've shown that the CDF, f of x, which is something you'll want to add to your distribution sheet for the exponential distribution. If we walk through the integration, we get 1 minus e to the negative x over theta. So then, probability that x, this is capital X, the random variable, is greater than little x is 1 minus the probability that x is less than little x. Again, these expressions are true for everything. And now we solve it, we plug in for the exponential distribution, and we get that the probability that x is greater than little x is e to the negative x over theta. Okay. So we can plug in now that, so I'm going to go back and rewrite this just to be clear for you, to write it again, that we have our conditional probability that x is greater than little x plus y, given that it's greater than x, is equal to the probability that x is greater than x plus y over the probability x is greater than little x. And then we plug in for our exponentials. And remember, we can decompose our exponent here for an exponential into the product, e to the negative x over theta times e to the negative y over theta. Again, if you multiply these, you add the exponents, so they're the common denominator theta, so they go back to this, but we're going to keep them separate. We're separating them because we have one of these on the bottom. We have e to the negative x over theta here, e to the negative x over theta here. They're canceling. And so we're left with e to the negative y over theta. I want to point out that this is the same thing as the probability that x is greater than y. This is called the memoryless property. And so it's the probability that a component will last at least x plus y units. Given that it's already lasted x units, is exactly the same as the probability that will last at least y units from here on. So it's constant failure rate, so it forgets that the component's already survived x units. It forgets that it's so far along in its life. So this is the memoryless property. It's also called a forgetfulness property of the exponential distribution. It's the only, so basically it starts over, and the exponential distribution is the only continuous type distribution with a support between 0 and infinity, that's important too, that has this forgetfulness or memoryless property, okay? So for the discrete distribution, we have the geometric distribution, and it has this property as well. I don't recall us going over it, but that's something that you can certainly look into and prove for yourself in the same method that we just did for this exponential, except instead of using integrals, of course, you have the summations for the CDF, and we talked about what that is and the probability that x is greater than k for the geometric p is equal to q to the k. We talked about that expression, so you see you have an exponent, nothing else, just an exponent for this expression, so the greater than, it's going to cancel out when you go x plus y over q of x. We're going to get q of x, q of y over q of x. These are going to cancel out, leaving us q of y, which is the probability that x is greater than y. So again, the same type of memoryless property for the geometric and the exponential distribution. Remember that the geometric is discrete, the exponential is continuous. So let's look at a second example quickly. So we're going to say, suppose an electronic component has a constant failure rate, and this is the part that I have added in for you that wouldn't normally be in a problem, and thus it follows an exponential distribution. If it says it follows a constant failure rate, that tells you right there that it's a exponential distribution, and it has a mean life of 500 hours. If the components lasted 300 hours, what's the probability it will last an additional 600 hours? So again, we're going to let x be the life of the component, so always define your random variable like this so that it's clear what x is standing for. That will keep it clear in your mind and make you better at solving these problems. You can say it's the life of the component or time to failure, which is the first occurrence in this case of the component. So theta equals 500, and so because mean life is time, okay, so we didn't give you the counts, average counts, we gave you the mean life, the mean time right away. So you have to be looking for that. You could be given the mean counts, or you could be given the mean time. And we're given the mean time, so that's theta, not 1 over theta, or not 1 over theta. And so I plug into the PDF. I plug in 500 for theta. There's my PDF. Again, I always write this down. That helps me, helps prevent me from making mistakes. And I said I want the probability that x is greater than 300 plus 600 divided by, or given that x is greater than 300. That, as we saw from before, is simply going to be the probability x is greater than 600. I plug that in, negative 600 over 500, or e to the negative 6/5. And of course, most of the time we want a decimal. I want to see this, but you can give me the decimal to 4 places for the probability, 0.3012. All right, so that has finished up our exponential distribution. Don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. If you have questions, come to virtual office hours. If you can't make it to that, then email me, but send me a picture of your problem and send me a picture of your work, and then I'll be able to help you. So I hope you'll take care of yourself and stay safe, and we will see you next time.